Alright guys, let's start with manometers now. So yeah, manometers, it has nothing to do with gender whatsoever, so don't get triggered. It's this device which is basically also called a YouTube. And again, it's nothing to do with the YouTube that we watch online. So basically it's a tube, literally shaped like a U. Simple as that. So what happens is, say we pour water into one of the arms. These are called arms, obviously. So you pour water into one of them, and imagine the water level moving up. So slowly this is going to fill up, right? So, and as it fills up, both sides will have the same height. So as I pour water into it, this would come up to, say, this level, and on this side it's going to come up to this level also. So you might ask, why is it that both sides have the same amount of liquid? Same level basically, and the reason is because there's a pressure acting down on this surface, which is basically atmospheric pressure. We usually denote it with A naught or PA, whichever one you're comfortable with. Here we're going to use A naught, and also this side is open to the atmosphere, so you're also going to experience atmospheric pressure on this side too. So basically both sides have the same amount of pressure, and that's why the levels are the same. So say what happens is, we take a U-tube as shown. Ooh, I'm getting better at drawing these. So, and say we connect a pipe to this, and it's connected to a gas supply. So what's going to happen? This is sealed. None of the air can escape along the sides here. This is tightly sealed. So this pushes the liquid down. Say this moves down here and pushes the liquid up to this side. Say it moves up here. So it moves down on this side. It moves up on the other side. And what you get is a height difference. So what this height difference represents is basically a pressure difference. Why? Because as I always keep saying, I'm going to say it again now, as you move deeper into a liquid, the pressure acting on you increases. So say for example, this is the surface of water. I'll just use a blue color so that you guys are aware that it's water. Let's draw it again here. So say this is water, right? Don't ask me what that is. And we have atmospheric pressure acting on the surface of the water. So say a point which is deep in the water, around here. Basically atmospheric pressure is acting here, plus we have this height which is causing perpendicular height, which is causing extra pressure, and we can find out the pressure exerted by this height, which is h rho g. So if you want to find the pressure here at this cross, or at this depth basically, what you have to do is you have to find the pressure due to h rho g, which is basically this entire height, plus you have to find the pressure due to a naught. So the pressure here, pressure at point x, say for example, say we call this point x or depth x, is going to be a naught plus h rho g. And say the pressure at x is this value. If we move up back from level x, the pressure will decrease. Why will it decrease? Because there's less water above you. Say we're taking this height now, so the pressure decreases as you move higher up. That's basically the concept of atmospheric pressure, and how it also relates to pressure in a liquid. So similarly here, going back to using a black pen, so similarly here what's going to happen is we have, or I could just use a different color, let's say red. Yeah, so say, is that red? That's kind of weird. It's a brownish sort of color. I guess it'll work. So say atmospheric pressure is acting here, so this is a naught, and that's the pressure here. Now what happens is, as you go deeper into the liquid, similar to the concept that we just saw here, the pressure here is going to be the pressure of a naught plus the pressure that you get due to this height h. Remember, this height depends on this side also. Basically this is the height difference. We're taking this point because, let's give them names, point level x, y and z. So the pressure at level x is going to be a naught. The pressure at level y is going to be basically the pressure of a naught plus pressure to this height of this liquid. So we can say a naught plus h rho g. H should always be in meters because your acceleration is in meters, and meters per second square. And the pressure at z is the same as the pressure at y because it's at the same depth. So we can also say the pressure at z is a naught plus h rho g, where h is the difference, height difference between the two levels of the liquid in the two arms. If they ever ask you to find the absolute pressure or the total pressure acting at z, what you have to do is basically a naught plus h rho g. If they ask you how much is the pressure at z more than atmospheric pressure, that's when you just tell them h rho g. Usually they'll give you the value of atmospheric pressure if they want you to find the total pressure, and if they want you to find the difference only, then they'll just give you the value of h, and from that you can calculate h rho g. Alright, so that's the basic concept of manometers. Let's go a little more in depth with it. So again, say we take a manometer. Alright, And so initially we start at the same pressure, same depth on both sides, and we connect a gas supply again, pushes air, sorry, so it has a higher pressure than atmosphere. This is going to move down. Say this moves down by 10 centimeters. As a rule, this must also move up by 10 centimeters because the volume of the liquid remains unchanged, right? So basically the height difference between these 2 points is going to be how much? 20 centimeters. Please keep this in mind that uh, the cross-sectional area, yes, I forgot. Please keep this in mind that the cross-sectional area of the pipe has no effect on these values. If you were to repeat this experiment with a fatter pipe with a greater cross-sectional area, it would not affect the height difference. It would still be 20 centimeters. All right? It's going to be the addition of this and this. So that's the basic idea. And again, the pressure here is going to be atmospheric pressure. The pressure at this depth is going to be atmospheric pressure plus H rho g. The difference between these two levels is just H rho g. Again, H being the height of the liquid, rho being the density of the liquid you're using, and g being acceleration due to gravity. Now, what would happen? What would happen if you repeat this experiment but with a different setup? This time what we're going to do is we're going to draw another YouTube. You thought I'd draw the YouTube logo, didn't you? Alright. Alright, that's getting ugly now. So we draw another YouTube and we connect this side to a partial vacuum. So it's basically a sucking machine. So it pulls the level of the liquid up to a certain height, doesn't pull entirely. And it creates this height difference between these 2 points, right? This is the height difference. So now, this is open to the atmosphere. So the pressure here, pressure acting here is A naught. So this is the pressure here, A naught. The pressure here then obviously is also A naught, even though there's no atmosphere here, but it's at the same depth. That's why the pressure here is A naught. Mind this, that the liquid is entirely all of this. This is all the liquid. So the pressure here is going to be less than A naught. By how much? By height h. Alright? It's going to be less than A naught by height h. So basically pressure again is equal to the atmospheric pressure here, which is A naught, but the pressure here is less. How much is it going to be less by? Minus H rho g. So that's the pressure at this point. Again, let's give them variables. Let's call this A, let's call this level B, and this C. So the pressure at A is A naught. Pressure at B, because it's at the same depth, is also A naught. And the pressure at C is basically less than atmospheric pressure by how much? H rho g. Boom, there you go. Easy peasy. This is how you use manometers, and this is how you do the calculations basically using these equations. And an important thing is that they sometimes ask what sort of liquid would you use. Usually manometers use mercury. So mercury has a density of 13,600 kg per meter cube. So this is 13.6 times more dense than water, which has a density of 1,000 kg per meter cube. And the reason we don't use water all the time is because it's too less in density. So which means if we look at the equation really closely, the manometer equation basically, or just pressure is equal to H rho g. If the density is too less, then the same pressure is going to create a really large height difference, which will limit either the manometer from, oh my god, now it's getting really bad. So it's going to limit the height to which the manometer can work, right? Say it can go up to this height difference, up to the very top. So it can't measure large pressure differences. It can only measure small pressure differences. So we only use water when we need to get good readings for small pressure differences. Because small pressure differences on mercury, the height difference would be so small you wouldn't even understand it, right? So if you use water here, then that difference would be larger. It's better to take the reading. So when the value is larger. So for low pressure values, we use water. When it comes to high pressure, water is too less in density, so the height difference will easily push the water out from one end. So instead of that, we use mercury. When we use mercury, the height difference decreases, hence you can measure greater pressure. Density higher, del H is going to be small. And another way you can design a manometer to measure larger pressure differences is basically if you use longer arms, if these arms are longer. So when you have longer arms, what happens is you basically can have a greater value of H. It's as simple as that. So yes, in summary of this, increasing the density of mercury, having a higher density of mercury leads to a greater pressure difference being able to be measured using a manometer. And that's why we use mercury. However, we sometimes rarely do use water. That is when you want to measure a small pressure difference, but you want to measure it very accurately. That's when you use water. And you can also measure high density, high pressure differences if you have long arms of your manometer. So yeah, that's basically the idea. And again, I'm saying this again, the cross-sectional area of the pipe has no effect, because if we just look at the equation again, H rho g, these are the only factors which affect the height difference or the pressure. So basically the pressure itself, height, density, and g. So yes, only if these values change, you're going to get a different reading from the same for the same pressure. Other than that, the thickness of the tube and these things will have no effect. So yes, in summary, manometers are devices which are designed to specifically measure pressure differences. You cannot measure atmospheric pressure with a manometer. Number two, atmospheric pressure will act on the end which is open to the atmosphere, and you measure pressure differences by connecting one of the arms of the manometer to your gas supply. Number three, the pressure difference will be basically H rho g, and you can find the total pressure by adding H rho g with the atmosphere. And if they just ask for pressure difference, H rho g is fine by itself. The lower you go into a liquid, the pressure increases. Number four, we use a manometer on this concept that the pressure is the same at the same depth. So basically here, for example, Y and Z will have the same pressure because at the same depth. Number five, manometers are not affected by the cross-sectional area of the pipe. And if the liquid goes down along one side a certain distance, it will usually go up the other side the same equal amount. All right. Number six, you can also use manometers to measure pressures less than atmospheric pressure, and the difference is going to be A naught minus H rho g. Using the same concepts, atmospheric pressure is going to be acting here, which is equal to the atmospheric pressure, which is equal to the pressure here, and this point will be less than that by H rho g. And number seven, the only factors which actually do affect the readings of a manometer are basically H, rho, and G, right? So basically H is the height, rho is the density, and G is the acceleration due to gravity. And for that reason, we sometimes use mercury if we want to measure large pressure differences, and we use water if you want to have a sensitive device which can measure small pressure differences nicely. That's it. We're done with manometers. That was quick, easy. Please do practice. You're not going to remember this stuff if you don't practice. So practice, 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 practice. That's what you need to do. All right. Keep going, guys. Hope you do good in your exams. If you need any help or anything, just shoot me a message. Message, nothing else. Bye bye.